Queensland is known as the Sunshine State with some of the highest solar potential in the world. But despite this, there is a fundamental issue in how we use energy. Even when we generate clean energy, we don't always use it as efficiently as we could. Large amounts of renewable energy are available at certain times and locations, but cannot always be delivered to where they are needed the most. The problem is not producing energy, but deciding how to use it in real time across a complex and constrained system.
Managing a large-scale grid isn't as simple as just letting electricity flow freely. Every second, the system must actively control dozens of interdependent variables to ensure safe and stable operation. For example, generators must continuously adjust how much electricity they produce. Batteries must decide when to store energy and when to release it. Power must be routed through transmission lines without exceeding capacity. Voltage and frequency must remain within strict limits to prevent system failure. And most importantly, total supply must exactly equal total demand at all times. This is not optional. Even a small imbalance can destabilize the entire grid. However, modern grids are becoming far more complex. Queensland's energy system is rapidly transitioning from a few large controllable power plants to a decentralized network of semi-scheduled renewable sources such as solar, wind, and batteries. This introduces significant uncertainty into the system. Solar output changes rapidly depending on cloud cover. Wind generation fluctuates unpredictably. Thousands of households both consume and generate electricity through rooftop solar. This creates a system with thousands of interacting variables that must be optimized simultaneously in real time.
Because of these complications, Queensland's current grid often operates inefficiently. Electricity is sometimes routed through suboptimal paths, increasing transmission losses. Renewable energy is curtailed, meaning solar or wind generation is reduced even when it could be used. And conventional generators may also be forced to reduce their output to maintain system stability. These inefficiencies increase operational costs for energy producers. These costs are ultimately passed on to the consumers, which contribute to higher electricity prices. Today, classical computers attempt to solve this optimization problem using probability-based heuristic mathematical models. These models simplify the problem in order to make it solvable in a short time. However, this approach has a fundamental limitation. It cannot reliably find the true optimal solution. Instead, it searches through a limited subset of possibilities and settles for a good enough configuration. As the grid becomes more and more complex, the number of possible configurations grows exponentially. This makes it increasingly difficult for classical computers to keep up, and the cost of suboptimal decisions continues to rise.
Quantum computing offers a fundamentally different approach to this problem. Instead of evaluating one possible solution at a time, quantum systems use principles such as superposition to represent many possible configurations simultaneously. They also use quantum entanglement to model relationships between different parts of the grid, allowing complex dependencies to be captured more naturally. In practical terms, this means a quantum system can explore a larger solution space more efficiently, increasing the likelihood of finding highly optimal configurations that classical methods may miss. We propose QGrid, a quantum-assisted optimization system designed for Queensland's energy network. It operates as a hybrid system combining classical infrastructure for data handling with quantum processing for optimization. It operates in 4 stages.
The first step is the input of data, where real-time data is collected from across the grid, including energy generation from solar, wind, and other sources, energy demand across different regions, transmission network constraints and capacities, battery storage levels and availability, and weather forecasts which influence renewable energy generation. This ensures the system has a complete real-time view of the entire grid. This data is translated into a mathematical optimization problem, which we define as variables representing generator outputs, power flows, and storage decisions, an objective function that aims to minimize energy loss and operational costs, and constraints that enforce physical laws such as supply equaling demand and limits on transmission capacity. This converts the physical grid into a structured problem that can be solved computationally.
Step 3. The optimization problem is then encoded into a form that a quantum computer can process. Using algorithms such as the quantum approximate optimization algorithm, the system represents many possible grid configurations simultaneously. Through a process involving quantum interference, Efficient configurations are reinforced, while inefficient configurations are suppressed. By repeatedly running and measuring the system, it converges towards a highly efficient solution across a very large solution space. This produces a set of optimal control decisions, including how much power each generator should produce, how electricity should be routed through the transmission network, when batteries should charge or discharge. These outputs are fed back into the grid control system. This process repeats continuously, allowing the system to adapt in real time as conditions change.
The benefits of this approach are significant. First of all, there's reduced energy waste across transmission networks, there's less curtailment of renewable energy, there's improved grid stability under fluctuating conditions, and there's also greater integration of solar and wind into the system, which ultimately, this system supports a more efficient and reliable energy system, which helps Australia progress towards this net zero target. However, there are important limitations that do exist. First of all, quantum computers are still an emerging technology with hardware constraints such as noise, limited qubit counts, and high operational costs. In addition, the accuracy of optimization depends on the quality of input data, which highlights opportunities for further research, such as improved forecasting and quantum enhanced sensing. And in the shorter term, systems like QGrid would most likely be developed in hybrid or regional applications rather than the entire grid by itself.
Queensland is already investing heavily in both renewable energy and quantum technology with companies such as PsiQuantum. By combining these strengths, we have the opportunity to lead globally in building intelligent, sustainable energy systems. The future of energy is not just about producing more power.
It is about using it smarter, and quantum optimization may be the key to making that happen. Thank you for listening.